them, provide some student perspective on some of the things that are going on in the class, and then I'll kind of wrap it up on where it's heading, some of the vision for the future of some of the possibilities for expanding this out down the road. So this is a class that started as a special topics class for 2 semesters, and this semester is the first time it's a permanent class in the university called physical computing. And I'll show how this ties into open source hardware in just a moment. But the first question you probably ask is, what is physical computing? What am I talking about with that name? What does that mean? Well, really, it's the bridge. It's the gap between looking at the digital world and the physical world. It's falling in between. So let me give you some examples of what I'm referring to here. So on the physical world, we might have everyday objects, clothing, could be art, something mechanical, some of the kind of anything you can touch and feel. And then on the digital side, we've got the web, software, databases, that kind of thing. So obviously, physical computing falls into the gap between those. And here are some examples. It could be referring to wearable computing. You're taking some everyday clothing, everyday, and bringing it to life by adding some aspect to it, like Google Glass, which we have, being demoed down in the lobby. It could be something like robotics, where you're taking like some physical object, like a car, and you're adding some software logic, you're adding something to it to bring it to life. Another aspect is 3D printing. You're using a combination of software and mechanical parts to create new physical objects. And also devices, alarm clocks, things like that, where you're having some sort of device that combines electronics, software, and some sort of physical apparatus. So that's what I'm talking about in terms of physical computing. And what we do in the class is we dive into these different aspects of it. Not so much yet on the wearable computing side, but for instance, we built a 3D printer this semester from a kit. Students constructed it. Anthony and Tony were involved in that process along with the rest of the class. And designing 3D models is something we're going to be doing in the next couple of weeks for actually creating custom designs and printing them out. A big part of the class, and actually this is open source hardware, by the way, because this printer is, what I mean by that is the design, everything about it is in the public domain for being able to basically replicate and construct something like that. We even dive into, would really be considered like open 3D models for what you print with it. You go out there and you can find the designs, you can find these 3-dimensional objects that have been created by other people and print them out. We've done that a number of times. A big component of the class, and this is really what kicked it off initially, what was really the starting point, was using something called the Arduinos. Arduinos are also open source hardware. It's a microcontroller, and what I mean by that is that's really like the electronic brain. You can program, you can write code, and students write code that controls electronic circuits. So this is used for embedded systems, things like that. Like there would be a microcontroller in that projector, in an alarm clock, in the camera, any number of things where someone has written software, pushed it to the controller, and then be able to operate things, bridge out into the physical world by collecting sensor information, maybe user input by pressing buttons, and causing some reactions to happen. So we dive into these different aspects of it in a little bit more detail as we go along. And as I mentioned, the 2 primary drivers behind the open source hardware aspect of it are the Arduinos and the printer body. This is a picture when we were building when the students were constructing the kit. I had another one, the one that I constructed as the learning process to get it up and running and going, and snap this picture partway through with a couple owls. I don't know how well you can see this being printed out. And that's an example of a model that somebody had created, put up on the web, downloaded, and had something just running as we were working on the project. So there's any host to you from going from using open source software to create these models over to ones that you can, tons of reusable things that people have put up on the web. So with that being said, I'm going to hand it over to Anthony to provide the student perspective, some of the projects and things that are going on in the classroom.
Hi, my name is Anthony. I'm an informatics student at the university. This is like my recap of my experience for the first half of the semester. So our first lab involved the Arduino board and creating like a circuit between like the board and the breadboard. It would be like simple enough, but you know, you're just plugging in wires here and there and creating a bridge between like the resistors so that it becomes a closed circuit. But for someone who like kind of never took an electronics course in college and barely in high school, I was completely lost and quickly humbled because I felt I had a lot to learn. And I don't like, you know, like I'm hindering my team. But after this lesson, through this lesson, I learned how the code that we work on our computers can be like embedded in the actual Arduino and constantly running like in sequence. So it kind of like bridged it all for me between like the digital and the physical. So before taking this lab, like I said, I lacked the concepts of how the physics and the digital combine. But after taking this lab, I kind of started to understand like where my interests lie more. I realized that although I did like the coding, I kind of liked the building of the kits more. So I started focusing on that as well. I did more research on like the actual electricity of it and understanding like why did we need ohm resistors and varying like levels of resistors. And along the way, we began to differentiate between like digital and analog and the importance of that. So it was very hands-on the whole time. Yeah, one of the most hardest things though is this. These are like schematics drawn out and like to like explain the flow of electricity, but I was completely lost. For like someone who's well versed, this seems like very, very simple. And my professor drew it out like 3 times for me, and I still couldn't grasp it. But basically, you can give anyone this drawing, and they can replicate this on that. And so understanding that for me kind of took a little bit of a few tries, but afterwards I kind of started practicing and drawing it myself, and I could understand like why each symbol represented a certain like aspect of the drawing. So this is kind of where I feel like is the most important thing. I feel like we need an environment on campus where people with varying levels of knowledge can come and collaborate with others who are well versed. I really like learning from others and people teaching me hands-on concepts. And I feel that an environment which is well funded and with well support can like really prosper. I feel like the future of our economy is going to be based by people who are self-made entrepreneurs, building things in their backyards and putting them on the web and selling them if that might be the process that they want to take on. But I feel like our economy is truly becoming more individualized and we're industrializing in our own homes, so it's very important. And I think this is Tony.
Hi everyone, my name is Tony. I'm a graduate student here at the University of Albany. I'm under the Information Studies program, and I was also an undergraduate student with the Informatics department as well. To go off on what Anthony said about the Blink project that we did, this is actually a little more advanced. As simple as it may sound, Simon Says project was very, very tough. It was probably one of the toughest according to John. So the concept here is basically you want to push a button so that it corresponds to the LED that it's connected to. But before you do that, you have to have the LEDs light up so that you can follow which one lit up first, which one lit up second, which one lit up third. So as you can see here, this is incomplete. This is when I first started out. I had no idea what I was doing, just like Anthony and the rest of us were. You know, we lacked the knowledge at the time to actually understand what was going on here. What do these little squares mean, and so on and so forth. And what Anthony was saying about how this board right here can just comprise of all source code that you want to push into it, that pretty much runs whatever's here, you know. So we go to the next screen. This is my partner's completed Simon Says project. You see the 3 LED lights right here, and you see the 3 buttons here. What happens is, once we run the code, we're going to see the light go up randomly in random sequential order, whether it's the red, green, and then yellow, or yellow, red, and green, and so on and so forth. You just want to press a button that corresponds to each LED light. Now, the only thing is that if you do it wrong, it's supposed to play a sound, whether it's a big beeping sound or anything related to that. But this is essentially what you would be looking at when it comes to the physical computing class when we're dealing with labs and projects. The LED lights, that's only the tip of the iceberg. There's way more to that than meets the eye. Like right now, we're working on a line following project, robot following project. Sorry. Basically, the robot is a car, and it's going to follow a black line that's drawn on a poster board. And the sensors have to pick up on whether or not there's light there or there's no light there. And it just follows it however you drew it. As far as the makerspaces and hackerspaces go, there is one out in Troy, but we strongly feel that there should be one here on campus, considering how huge the UAlbany family is. To start things off, I'd say that we can start off something as small as creating a club, for people to share their knowledge and whatnot. As far as getting the actual physical machines go, people can donate to us. Anyone who has any sort of e-waste that they want to get rid of, but they don't know how to properly get rid of, they can donate to us in school, and then we can funnel that through the proper chain of command and so on and so forth, so that people don't actually have to worry about breaking old equipment or even new equipment, depending on how new it is. But yeah, that's great.
Yeah, so I definitely appreciate getting the student perspective to share this with me and the rest of you to see how it's been adapting over the course of the semester and from where they start to where they end up. And that's where I'm going to kind of lead into now, is to talk about, well, where is this heading? What are some of the possibilities? In terms of where we want to kind of provide some emphasis of where this could go, and also show some examples of what, on the innovation side, what some student groups have done in prior semesters, where these guys would get in the rest of the class by the end of the semester. So we've still got a ways to go as we dive into more, larger integrated projects, and I'll show some examples of some ones that have been done before. Driving innovation is a big part of what I want to do more of. And as part of that is bringing in diverse perspectives, having collaborative opportunities where you get some people maybe in the business side, bringing some ideas of what value does this generate, of what somebody can build that is more integrated in with some sort of like a business plan or some more on the entrepreneurial side. It could be other departments. If some students are really interested in the arts, there could be, what can you do that kind of is more of a kind of modern art side where you're having electronics or having something more interactive. So you can see how there's a lot of different areas in which it could connect. There's a lot of possibilities, and so that kind of collaborative opportunities and identifying those and developing some of those partnerships is something I'm interested in. Also trying to have more comprehensive course projects that cut across the semester. Let me give you an example. Tony mentioned the line following robot. What that is that is a bot that the students write the software for and the design electronics, and it will follow a black line, so it could follow a course, using some sensors to detect whether or not it's over the black line or not. A couple sensors so it can change its direction. What I want to do is have the 3D printing aspect, which is new to this semester, where students actually print out their own cars and then compete them versus each other. So they do the construction of the car from a 3D print for the custom model, the design software, the design electronics, the full shebang. We are doing that this semester. We're doing it in reverse order because the 3D printer is new. We're actually going to be designing the cars in the latter part. And we're going to have a competition, friendly competition this week, where the students they all have their different bots, see how well they compete versus each other in different categories in terms of speed, accuracy, and creativity. And from last semester, some students do some really, really creative stuff. To give an example, I've had one group create smartphone controlled car. So this one was not using sensors to detect the line. They actually did it through a mobile app, and it was communicating over Bluetooth to control the car. So these are real pictures from the class. I have a YouTube channel up as well that has the different projects that I've recorded over the course of the last couple semesters, along with some of the projects. So this is just a couple examples. I think if you Google, like or you're on YouTube, and you like University of Albany physical computing or anything like that, you should be able to find the channel. So it's got a whole bunch. So here are some of the examples. Another one was somebody created a exerciser for dogs. This used a couple of the Arduinos, in which it would basically hit a problem that his dog would just get stir crazy. You wanted to basically tire his dog out while he was at work. So this would basically, this is using M&Ms, but it could be dog treats or dog food. And it's making noise, and it would basically get the attention, spread these out around the house, and get the attention. The dog could come and be trained to hit a button, and then it would release a little bit of the food. And these things would randomly, make noise at different times or different places around the house. So the dog's running around the house looking for it. So it's not, crazy when he gets home. We had another group created a Twitter bot. This you can take any different sensors. Really, you do a variety of different things. But the heart of it is it will automatically push information to Twitter. So it could be collecting something about the environment, whatever you want, and it'll post it to Twitter on either predefined intervals or whenever something interesting happens. And then we've had other ones like alarm clock here, using kind of these different custom tubes that the student was in that group, somebody was very interested in these, and they actually, I think, came all the way from Russia to get these particular parts to be able to integrate in. So this is, I encourage you, if you're interested, to look at some of the other ones that people have created. This here, so last semester we didn't have the 3D printer, but towards the end of the semester, because we had some, as was mentioned earlier by the students, we got to there's a makerspace over in Troy where people have access. You can go in, you have access to all sorts of equipment, 3D printers, wood cutting machine, all sorts of build just about anything. We went there on a field trip last semester. This time I have one of the co-founders is coming in actually on Thursday to talk to the class before we lead into the whole Robotics Olympics for the competition aspect of it. But last semester, so students had seen the 3D printers in action over at the makerspace. We didn't have access to one ourselves on campus. But I had the students create models using some software to create these 3D models that could be printed out. Well, once I had access to a printer, I took one of those models and printed it. And so here's an example of me filming the print that one student created last semester, assuming it works. So this is the 3D printer in action. I won't worry about sound, but the sound's kind of cool. Here the thing go. This is a logo for the course. So the student created one that had the Arduino logo, and it's an INF 470, 570 in physical computing. So this is where it's partially built. It's just writing like the letters and everything. So it's probably not the best. It's not as easy to see right here because it's a little dark, but it'll give you the basic idea. It takes a long time to print something. So there's the printer. And what's really interesting about this though is, so it's, like I said, the students built this printer. This is the one I built. They built one the same model from a kit. And that was, what was interesting about that is you really get to see something from such a low tech coming together. Like it really, the printer is made out of wood, it's held together with zip ties, and some really basic parts, but you're able to integrate it and put all these pieces together and do something really cool, like in my opinion. And here's another example. So this is the Robot Olympics from last year. So, I mentioned the the competition in line following robots. This is one from last semester, which will be happening again this time around, this week. I'm sorry, Wednesday. This is the bot moving around. So this is where this group was really creative, and that they actually use more sensors to try to compete better to have the thing be more accurately following the line by using a host of sensors along that plane there. And actually, so it's not perfect. It went off track there and then stopped, but you can see that they try to kind of look for different edges for how to kind of outperform each other. So that being said, we want to take some questions in the little bit of time we have left. This is just some examples. This is some pictures taken from during the construction of the open hardware 3D printer.
So for the 3D printer that you have, when it prints something, is it making an imprint on some kind of object, or is it actually printing out the object itself?
It's printing out the object itself. It builds in two-dimensional layers. It'll build a host of layers up. So it starts, it's these little tiny thin layers will be on the base, and then it just slowly raises up, builds the next layer, raises up, builds the next layer. So things, give you an example, things that are difficult to print, if you had something that had like an overhang, like if it was like this, you had no support, that wouldn't work because you're building from the ground up. Now there's things you can do to kind of try to build something like that, but those are the words that's more difficult.
How long did it take to construct the kit?
So let's see, I think the construction of the printer took about 8 hours with the class. It's a lot of small parts, Actually, the printer's only $300 though, if people are interested in picking one up. Well, I think the latest model is $350 because they added some new things. But it took about 8 hours for the construction, and then you're kind of looking at another 5 maybe before you're able to really get your first print, because you got to do with the software configuration, you got to fine tune it. Both the one I built and the one the students built, same thing. Before it actually printed something successfully, you have to retake part of it back off and tighten something and then put it back. It's not that bad, but you got to kind of go through that process. So I say it's probably roughly 8 hours for the physical build, and then another 5 of software and fine tuning before it's